Hi student, welcome to Learn Chemistry with Emerald, and in today's class we are going to be looking at measurements in chemistry. We'll look at the units of measurement, the scientific notation, significant figures, and percent errors. Let's quickly do a teaser here. Put the following units in order from smallest to the largest. The meter, the centimeter, millimeter, kilometer, at one point, at one end, kilogram, centigram, milligram, gram, liter, microliter, picoliter, kiloliter. Please put them in order from the smallest to the largest. Put those meters separately, the 1 and 2, 1 to 3 separately. Okay. Now, let's quickly look at selected units. We have the mass, we have the meter for length, the gram for mass, the Pascal for pressure. You can also have ATM, that's atmosphere, for pressure as well. It's one of the accepted SI units. Then you have Kelvin for temperature, mole for amounts of substance, joule for energy, work quantity of heat, seconds, minute, hour, day, year for time, liter for volume. You can also have centimeter cube or decimeter cube, that's cm cube and dm cube for volume, parts per million for concentration, molarity for solution concentration, AMU, that's atomic mass unit for atomic mass. Others, you can also, another work to give you, another assignment to work with, find more SI units and the quantity that they measure. Their symbols, their name, and the quantity they measure. Okay, let's go back to the teaser I gave you at the time. We are asked to put the following units in order from smallest to largest. Let's start with milliliter. The correct arrangement should be milliliter, centimeter, meter, and kilometer. The next one is milligram, centigram, gram, kilogram. The next one is picoliter, microliter, liter, and kiloliter. Now, what information do these prefixes centi, milli, kilo provide us? What are the information that they provide us with? Okay, let's move on. The factor is 10 raised to power 3. Anything 10 raised to power 3 is kilo. Anything 10 raised to power minus 4, minus 1 rather, is deci. 10 raised to power minus 2 is centi. 10 raised to power minus 3 is milli. 10 raised to power minus 6 is micro. 10 raised to power minus 9 is nano. 10 raised to power minus 12 is pico. We could have more. We have tera, etc. So these are units that you should know. Okay, so let's move on. All these prefixes and others you should know. Please make sure you know up to 10 raised to power 6, from 10 raised to power 3 to 10 raised to power 6 to 10 raised to power 9 to 10 raised to power 12 as well. Please find out about them. That makes it 2 assignment now, right? So go and find out about them. Now let's quickly talk about scientific notation. When studying chemistry, it is common to encounter very large or very small numbers. There is a system that we need to use to shorten long number chains, and that's why we introduced scientific notation. So in scientific notation, the long chain numbers are written in form of m times 10 to the power n, m times 10 to the power n. The scientific notation is simply a number times 10, a number times 10 raised to power an exponent. M is a number greater than or equals to 1 and less than 10. Okay, then n is the exponent, the nth power of 10. It can either be positive or negative, and it represents the number of decimal place that is moved. Okay, let's look at a practice question here. You have to convert the following scientific notation to their usual form. You have to convert the scientific notation to their, this is a long number, like we have said, m. So the m there is 6.39, and then times 10 raised to power n. So the n here is minus 4. The same thing, the m here is 3.275 times 10. The n there is minus 2 8.019 times 10 to the power 10 raised to the power, times 10 to the power minus 6. Okay, so let's look at them. If you convert the following from their scientific notation to their usual form, this is their usual form now. 6.39 times 10 to the power minus 4 is 0.000639. 3.275 times 10 to the power 2 is 327.5. You know, is we are saying 3.275 times 100, it will give you 327.5. That's 10 to the power minus 6. That's 8.019 times 10 to the power minus 6, or times 1 over 10 to the power 6. Okay, it will give you this value. Now, where does scientific notation comes in? If you notice that this is a scientific notation, you have converted them to their usual form. Okay, now it is better that we put it in scientific notation because it makes it much more presentable, and it aligns with the information as given by the science model. Okay, so it is important that we put them to their scientific notation instead of their usual form. Why? Because it makes it more scientific, and it makes it even more presentable. Because these numbers are large, it is better we put them in scientific notation. So quickly, let's look at a practice question to do. You have H43.4, you have 0.00421 and 1.54. You have to put them in scientific notation. Pause this video, put these numbers in scientific notation. Let me see what you are going to come up with. Let me see what you are going to come up with. Now, if you have done it very well, the first one will be 8.434 times 10 raised to the power 2. Why? Because in expressing them in scientific notation or in standard form, so it's the same thing. This scientific notation is the same thing as your standard form is in mathematics. Okay, so you are just having what's it called 843.4 times 10 raised to the power 2 or times 100, which is 10 raised to the power 2. Then the next one is you count the number of zeros 1, 2, 3. So you are going to have 4.21 times 10 raised to the power minus 3. Then 1.54, you are going to have 1.54 times 10 raised to the power 0, or just 1.54. 10 raised to the power 0 is 1. Okay, so that's how you get that one. Now let's move to the notation sheet. When converting standard notation to scientific notation, now this is what you do. If the number is 1 or greater, you have a positive exponent and move the decimal to the left. Now check the information provided here. From that, immediately after that decimal, you are going to have 1, 2, 3, 4, 5 before 8. Immediately after decimal, please now the first thing you need to know is that, like we have said, if the number is 1 or greater than 1, you are going to have a positive exponent. Okay, it is when the number is less than 1 that you are going to have a negative exponent. Okay, in this case, this number is greater than 1, so you are going to have, okay, as we were saying, we are having immediately after the decimal, we count 1, 2, 3, 4, and 5. So immediately after the decimal, we count 1, 2, 3, 4, and 5. So you are going to have 801236.98. Now, if the exponent is negative, that means it is smaller, less than 1. You move the decimal to the left. So you are going to have 0. Of course, is 10 raised to the power minus 5. So you are going to have 0.005. 0.0000508. Please look at it very, very well critically again, and see how we did that. Now let's really talk about significant figures. We look at notation. Take a lot of questions to work on the notations. If you are measuring this Ghana block in inches, what would you determine its width to be? If you are measuring it in inches, what do you determine its width to be? Let's go. In measurement, there is always some amount of uncertainty. Now, the significant digits in a measurement consists of all the digits known with certainty plus one final digit, which is uncertainty or is estimated. We usually have in a particular digit, we have one that is certain, then we have uncertainty added to it. Repeating a particular measurement will usually not obtain precisely. The measured values vary slightly from one another. For instance, there is a difference between precision and accuracy. There is a difference between precision and accuracy. Now, precision refers to closeness of a set value obtained from identical measurement of something, while accuracy refers to closeness of a single measurement to its true value. That is the difference. Look at this board the example we gave here. Now, if you check the first one, they are both accurate and precise. Accurate in the sense that is close to the closeness to its true value. It is the inside. The center point is where we are targeting, and it's and it hits the center point immediately. Now, precision, it is precise also because each of the set of values, each set of value obtained from magnetical is very close, and it's even close. All the three are close, so they are precise and of course and accurate. One hit the center, others were very, very close. So the one that is hitting the center is accuracy. The one that are very close, the other two that are very close are precise. So they are precise and accurate. Now check the second one very well. You will notice that they are accurate, but they are not precise. Now one of the measurement is hit the center, so accurate. However, the other ones, they were not close at all to the center, to not precise. So this is accurate but not precise. Now if you check the other ones where you have precise but not accurate. Now you will notice that the three of them were are a bit closer to the center, but none of them is accurate. None of them hit the center. Then if you check the fourth one too, neither accurate nor precise, because all of them are far away from the center value, and of course none of them hit the center value. So if in significant figures, you want to look at precision and accuracy. Now, for rules of significant figure, the number of digits reported for the value of a measured quantity. All non-zero numbers and zeros between are significant. All non-zero, like 9, like in this case now, 909, they are significant. 1002 significant. All non-zero numbers and the zeros in between them are significant. Please take note. Then zeros at the beginning of a number are never significant, like this one. Zeros at the beginning of a number are never. That means that for instance 0.0000912, all the zeros are not significant. The significant figure starts from 9. So the significant figure here start from 9. The same thing applies to 0.01 here. The significant figure start from 1. In the third one, the significant figure start from 1 as well. 1001. Those ones are significant. The significant figure numbers here are 1001. those ones after the other zero. Zeros at the end of a number are significant only if a decimal is present and to the right of the decimal. For instance, where you have 0 900.0, 900.0 is that point zero is significant because decimal is present and is to the right of the decimal. Okay, so let's move on quickly. Significant figures in calculation. You can see it from here 0.250. Of course, you say if it's starting from zero, it's not significant. So the significant figure here is 250 here, 250. And the second one, the significant figure is 186.5. We have we have significant figures there. Okay, let's quickly go to percent errors. For percent errors, the formula is percent error is equal to your result minus accepted value over accepted value times 100. Sometimes when we do calculations, sometimes we are far off a measure value. So percent errors help us to determine how far we have gone off a true or accepted value. When our measure value has deviated from the true or accepted value, the percent error helps us to see how far we have gone from that accepted value. And this is the formula. Let's take an example. A student measures the volume of a piece of zinc by water displacement to be 75.0 centimeter cube and the mass to be 562.5 gram. Of course, you know that density is equal to mass over volume. Density is equal to mass over volume. Now let's quickly check the density. The density as measured here is 7.5 gram per cm cube. 7.5 gram per cm cube. Now let's look at the reference table to see how far we have gone from the accepted value. Okay, now if you check very well, the density, the accepted value is 7.134, 7.134, and ours is 7.5, 7.5. So the accepted value, the measure value is 7.5, the accepted value is 7.134. Now, how do we calculate the percent error? Percent error is your result minus accepted value over accepted value times 100. Now, this is how you do it. You will see 7.5 minus 7.134 over 7.134 times 100. That's 5.1. 5.1. So the percent error here is 5.1%. So you can take other calculations to calculate their percent error. Now all of these measurements, the percent errors, the significant figures, the scientific notations, and the units of measurement are all important when you are doing chemistry calculation. So you need to pay rapt attention on them. We can take more exercises to work on and see how better off you are. Now you are building a foundation for yourself in terms of calculations in chemistry. I hope you enjoy the class. Continue to learn chemistry, and bye bye.